Okay, so what happens on a torus? So let's try to draw a graph, an embedded graph of the kind that we were wanting on a torus. So the way that we are going to do it is we are going to, oops, this was so the color for an edge was green. So let me start with this curve, embedded curve here. Let me put 3 vertices here. You can put any number, right? And now let me put these edges in. Okay, that goes around like that. And these are, so if I put these 2 in, then this bounds this region, right? So this region is something that you can sort of flatten out to be something that, sort of looks like something on the plane that's bounded by sides all around. Okay, so this certainly it's just like a rectangle, right? When you sort of flatten it out. Okay, so that's a valid region, and you can do the same. You can add another edge here maybe, and then you get this region here, and then there is another region that kind of goes around and sort of wraps and sort of into the whole. So you get these 3 regions, and everybody sees 3 regions, right? So in other words, what happens to the number of vertices? The number of vertices is 3 in this case. Number of edges. Okay, so let's count the number of edges carefully. So we had this, we added these 3 guys, but then in between these red guys, there are 1, 2, 3 edges, right? So there's a total of 6 edges that you see in this picture, okay? And the number of regions, as I said, is 3. Number of regions is 3. So it turns out, and this is a fact, we might get to it later on, is that the Euler number of a torus is 0. Okay, so no matter what graph you embed on a torus, okay, so I should say a little bit more about region being. So region, you necessarily need to be able to flatten out. So for example, if you just draw maybe a triangle or something, okay, so on the torus like this, well, the inside region is definitely a valid region. So this is a valid region, right? So that is something you can see that you can flatten it out in the plane. But so the complement is not a valid region. Okay, so this has this some kind of funny, this hole in it, which you're not really sure about whether it's, something or not, or, so this is not a valid region. So you want the regions to be sort of pieces that are just in a planar case. They're sort of actual regions that you can sort of flatten out on the plane, right? So it's sort of, sort of just like before, okay? So, so whenever you have that, by any graph that breaks up your torus into valid regions, you do the Euler number formula and you always get 0. And not just for any torus, the point is that you can do it for any, let me use another color. So any surface or any surface topologically equivalent to a torus, right? So topologically a torus. Okay, so let me sort of quickly show you an example of something which is topologically equivalent to a torus. This is this one. Okay, so can everyone see this animation? Yeah, so everyone is familiar with this fact, I suppose, that for a topologist, a coffee cup and a donut are the same, and well, this animation is kind of useful. Right? So let's go back to, oops. where was I? Okay, so here, right. So where were we? So you had something which is topologically equivalent. Okay, so I think it. So we lost something. It's probably crashed or something. Let me sort of write it again. So anything topologically equivalent. So any surface. Let me say any surface. So this Euler number turns out to be a topological invariant, right? So it's topologically equivalent. It classifies surfaces. Okay, this is something. One of the things that when one learns algebraic topology. Okay, so this is in fact sort of so in topology when you learn it, there are sort of a couple of different parts to it. By the way, a coffee cup for a mathematician is actually a sphere with a handle. Okay, so let me. So a coffee cup is a topologist. You will say that a coffee cup is a mathematical way of putting it is a sphere with a handle, and the way that a topologist will draw it is this is a sphere. And there's a mathematical notion of what a handle is. It's a circle cross an interval, so which gives you in this case, it will give you some kind of cylinder, right? And when you attach it, that chap is homeomorphic, or topologically equivalent, right, to a torus. Okay. So this notation here, this twiddle equal to just means topologically equivalent. Another nice way to visualize a torus is, so another depiction or another way to visualize something which is topologically equivalent to a torus is a square with opposite sides glued. Okay, once again, these can be made very precise, and you'll be doing it. So when you read more about what quotient spaces are, you'll understand what I mean. That this guy, you take a square, and if you glue this side to that, and you glue this side to that, and by glue I mean that so you are identifying. So if you are an ant, and you kind of walk out this way, you'll come in that way, right? Because these 2 points are just opposite points, this side and that are the same, right? After identification, right? And so when you do that, you get a torus. The same for the top and bottom, right? So this is one way to see it, right? So when you glue one pair of opposite sides, you get a cylinder, and then you glue the other pair, then you get a torus, right? So this is one way to visualize it. So you start with the square, and then gluing this pair of sides gives you a cylinder, gluing the other pair gives you a torus, right? So this is a very standard construction, but this is going to be very useful for us all the time. Okay, so all right, so okay, so this is a torus. And so let me try to draw that graph we had before. So this guy, okay, so in this picture, okay, so we can do that. So here we can let me erase this ant. He's no longer needed. Okay, so this guy, this edge I've drawn is actually a closed circle, right? Because the top point and the bottom point are the same after identification, right? And then we had 3 vertices on this closed circle, and then we had added these edges, which again are, sort of connect up, right? These are actually, each of these are one edge. So I've got added these 3 more edges, and then the regions that we had marked. So this region So this left part was this going back to this. And so this is one region and this is another. And then this here, the top part here is actually the same point as here. So in fact, if you think of these green lines as walls, you'll find that these four regions in these corners actually are sort of one connected region, right? So this is one way of visualizing. It's easier to visualize this, or at least once I find it easier to visualize than trying to visualize what happens in this 3-dimension and so on, right? So here you are working with a flat piece of paper and it's easier to visualize. So exercise. So on a torus, so this is maybe an easy exercise. You can embed K5. You can embed K5 in a torus. All right. By the way, I'll send out these. I'll give these sort of set of exercises or things to think about, and maybe next time we'll kind of have a look at what people have thought about and about these, whether they've solved them, and if you have questions or sort of trouble, you can always let me know. But these are sort of things that you can do to make this course so that you can learn more from the course. A slightly more difficult exercise would be you can also embed a K6, a complete graph 6 in a torus. Okay, and then you can see how far you can go. Okay, can you embed K7 in a torus? Okay, what about K8? Okay, so so number of edges grows very rapidly. So I wouldn't recommend you kind of actually, but you can, so if you have a free afternoon or something and you're, stuck at home, as we all are now, you can try to sort of play around and see what you can do. And so this is something that one can, this is one exercise that you can sort of amuse yourself with. Let me also, so that the final thing I want to mention is that sometimes, so the thing is that, so the way it will work, I'll give some references at the end. So you'll read up some of these notions like, topologically equivalent, what it means, and so on. What are surfaces, for instance, things like that, and then I'll try to supplement it with sort of more examples and so some kind of questions of interest, perhaps exercises which are fun to do, things like that. But I guess the onus is on you to kind of sort of read and sort of learn. Let me sort of mention, before I give you the references, let me mention one last thing is that, sometimes Euler's theorem, if you look up, on maybe on the internet, Google or something, the Euler's theorem is called Euler's Polyhedral Theorem or Polyhedron Theorem. Okay, Polyhedron Theorem, or Euler's theorem for polyhedra, and this polyhedron, oops, it's an N here, right? So what's a polyhedron? Well, you are all familiar with some of these, right? So there's a tetrahedron. You can have a cube. Various other shapes are possible. So let me sort of give you another glimpse of. So these are all possible sort of different polyhedra. So all of these are topologically a sphere. Okay, so I'm going to. So Euler's polyhedral theorem is about things which are topologically. Oops, it crashes every time. I need to fix this. So Euler's theorem is always about. So oops, we've lost those, but it's something that is topologically a sphere. Okay, so I'm going to say it's actually a convex. Sometimes they're called convex polyhedra, or let me just say topologically a sphere. And let me draw a cube again. It's probably the easiest to draw. Slightly more difficult would be something like a dodecahedron or icosahedron. So the point is that in Euler's polyhedron theorem says the number of vertices minus number of edges plus the number of faces is always equal to 2. So this time, I mean, these regions are these flat polygons, right? So these regions are in fact sort of polygonal, right? These are the faces of this solid object, right? So so this is the same as what we sort of talked about for planar graphs, because the edges of a polyhedron form a planar graph, right? So note that, why is it the same as what we were talking about? The edges, the edge graph of a polyhedron is planar, right? And one way to see is that if you think of this this polyhedron that I've drawn here as a wire frame, and then if you just lower some light bulb, right, on it, then if you look at the shadow of this wire frame, right, so you'll get a planar graph on the plane, right? And that's exactly sort of capturing how the sort of edges and vertices of the edge graph are connected, right? So you can flatten, if you have this topologically a polyhedron which is topologically a sphere, so let's say it's convex, right? So then when you flatten it out by like a shadow, this is called a stereographic projection, right? You might have already seen it. So this you get a planar graph, okay? So here's another exercise. The exercise is, give an example of a planar graph. So come up with a planar graph that is not an edge graph of a polyhedron which is a sphere, right? A polyhedron, let's say it's a convex polyhedron, okay? And let me tell you about, if you drop the requirement that a polyhedron is convex or topologically a sphere, there are such objects, okay? So let me once again crash this. I want to show you another. Let me see if I can do it without crashing. It was working fine before. So this is an example, right? It's topologically a torus, right? But it's an object built out of these faces, which are polygons, right? Euclidean polygons. So you glue it, but it's topologically a torus. Okay. Oops. Right. It crashed again. Okay. So so here's an unsolved problem, right? In mathematics, we often have these. So the unsolved problem is what graphs, this is something actually in graph theory, I would say. So what graphs are edge graphs of let's say, let me call it non-convex polyhedron. Let's say something which is topologically equivalent to a torus, for instance. I think even that is probably not solved. Okay, so any case, yeah. So I just wanted to say that Euler's theorem is often, sort of talked about in connection with polyhedra and not just planar graphs, and all these things are intimately related.